Hi everyone. Today we're going to be talking about solubility rules and how we use them to determine whether or not we're going to have a chemical reaction work to completion, what products we're going to form, and also what states of matter those products will be turning into. The other things that we're going to be able to do as a result of this lesson is to predict what compounds we will form in a double replacement reaction, and also whether or not those products that we form are soluble or insoluble. So we'll talk about all this stuff in a second. So when we use the term soluble or insoluble, what we mean is whether or not it will dissolve in water. If we call something soluble, that means it will dissolve in water. And when we write this in the formula, we label it AQ behind what the formula for that chemical is. So for example, I might write sodium chloride AQ. What that indicates to me is it's sodium chloride that is dissolved, what am I writing here? Dissolved in water. So if I see that I have a chemical formula and you see that little AQ sign behind it, what that means is it's a solid that has been dissolved in water. It's something that's soluble. On the converse, if we have something that is insoluble, something that will not dissolve in water, we will label it S for solid in that chemical formula. So for example there, we might see something like lead sulfate, okay? Lead sulfate does not dissolve in water. So lead 2 sulfate, and this is an insoluble product. So when we form this, you'll see that insoluble stuff just sort of sticks together at the bottom of a beaker. It separates itself, whereas a soluble material will totally dissolve and spread itself out. So how do we know what's going to be soluble and what's going to be insoluble? Well, we have a lot of rules. So you do not need to memorize these rules by any means. You will be provided with these. You just need to know how to use them and how to identify whether or not something is going to be soluble or insoluble. So as we look through here, if we see rule number 1, all nitrates and acetates are soluble. That means any time that you have sodium nitrate, calcium nitrate, potassium nitrate, whatever nitrate you want, whatever acetate you want, it will always be soluble in water, always be aqueous. And then the rules go from there. We have some exceptions. So if you note here, like number 2, all chlorides, bromides, and iodides are soluble except those of silver, mercury 1, and lead 2. So you just kind of have to read through the rules. Oops, I didn't want to highlight that. You just kind of have to read through the rules and see whether or not they apply to something that you're looking at. So let's try some examples. So I'm going to look back and I see rule number 2 says all chlorides, bromides, and iodides are soluble except those of silver. Some hydroxides. So let's look through the list and see where we find hydroxides. Number 6. Okay, so rule number 6, all oxides and hydroxides are insoluble except those of alkali metals. So because it's that exception, right? So the alkali metals are the exception, and we see potassium. Potassium is an alkali metal. So I go back here and I try to look for sulfates. So rule number 3 is all sulfates are soluble except barium, strontium, lead, calcium, and silver. Last one, we have a nitrate, NO3, and all nitrates and acetates are soluble. So if we look at this first one, we have AgCl. And we're going to mark whether or not it is soluble or insoluble. So we have a chloride here. This is silver chloride. So that means it is insoluble, and that is rule number 2. Okay, so I'm just writing that on there so you know why I'm choosing these answers. The next one we'll look at is KOH, potassium, right here, so the KOH. That means is that this is aqueous. It's the exception. Typically, if we had a hydroxide, it would not be soluble. So let's look at our next one. We have zinc sulfate. So zinc is not one of those, meaning it's aqueous, okay? And no exceptions. So that is aqueous, okay? So, yeah, you just pretty much have to be able to read the rules and see what it produces. So really quickly, I want you to pause the video wherever you're at and try to utilize those solubility rules to determine whether or not it is soluble or insoluble. I'm just going to really quickly go through these as to why they are that specific answer, just so you have an explanation. But the first one, we have HCl, so that's hydrochloric acid. If we look, let's see here, rule number 2, determines that this is aqueous, okay? Barium sulfate is one of the exceptions to rule number 3, so that one is going to be a solid. Sodium hydroxide is a hydroxide of an alkali metal, so it is aqueous. Iron chloride, if we look all chlorides except silver, mercury, and lead, that's not one of those exceptions, so that's going to be aqueous. Let's see. All sulfides are insoluble except those of alkali metals, alkaline earth, and ammonium. That's rule number 7. So that means this is going to be a solid. If we look at this next problem, the calcium nitrate, all nitrates and acetates are soluble. So this is going to be aqueous, okay? The next one, we have a chromate. So all phosphates, chromates, and carbonates are insoluble except those of alkali metals and ammonia salt. Potassium is an alkali metal, so this one is going to be aqueous. And then the last one we have is calcium carbonate. Carbonates are rule number, where am I? They start to all blur together. So we can actually find the answer to that in rule number 8. All phosphates, chromates, and carbonates are insoluble except of those of alkali metals and ammonium salts. Calcium is not an alkali metal or an ammonia salt, so this is going to be solid, okay? So that's where we're at kind of right now. So when do we actually use these solubility rules? It mostly has to do with double replacement reactions. In a double replacement reaction, you know that your metals are going to swap partners. So at the beginning, we have sodium chloride and lead nitrate. They're going to swap partners, and we are going to form sodium nitrate as well as lead 2 chloride, okay? So this is going to be important. When we look at these double replacement reactions and the products that we form, we want to be able to figure out whether or not those are going to be aqueous products or solid products. So let's look at this example. That's what we just did before. We have the sodium chloride added to the lead nitrate to form sodium chloride and lead nitrate combined to form sodium nitrate. So I'm just going to write those products in. And lead chloride. Okay, so those are our 2 products. If we see, this is an important note, when we make our products, if we see that there is no precipitate formed, meaning no solid, it's not going to happen. The reaction is not going to happen. In order for the reaction to happen, you need to have 1 aqueous and 1 solid. That has to be the requirement. So if you don't have any solid that's being formed in a double replacement reaction, you don't have a reaction. It doesn't happen. You just mix 2 things together and they sit there. So at least 1 thing needs to be a solid in a double replacement reaction. So let's look through our rules. We have sodium nitrate for our first one, and I see rule number 1. All nitrates are soluble. So I'm going to put an AQ here for aqueous, meaning it dissolves in water. Then I have lead chloride, and that's rule number 2. All chlorides, bromides, and iodides are soluble except for those of silver, mercury 1, and lead 2. Well, this is lead 2, so that's the exception. It's a solid. So this reaction does go to completion. Let's try another one. So now we have iron nitrate reacting with sodium hydroxide. The iron goes with the hydroxide, the sodium goes with the nitrate. So I'm going to form sodium nitrate, and I'm also going to form iron 3 hydroxide. Okay, so now I'm going to look at my rules. I remember from the last one, rule number 1, any nitrate is going to be soluble. So I know this is going to be aqueous. And if I look for the rules for hydroxides, that's going to be found in rule number 6. All oxides and hydroxides are insoluble except those of alkali metals, ammonia, strontium, barium, or calcium. And iron is not one of those exceptions, so that means it's going to be a solid, and this reaction is going to work and go to completion. We'll try one more together. So we have potassium carbonate reacting with magnesium sulfate. Potassium will go with the sulfate. Magnesium will go with the carbonate. So I'm just going to write that over here really quickly. Potassium sulfate plus magnesium carbonate And if we look at the states of matter here, if I look for the rules for the potassium sulfate, all sulfates are soluble except barium, strontium, lead, calcium, and silver. This is not one of those, so it's aqueous. All right. And then we have magnesium carbonate, and my rule here is, let me find it. All phosphates, chromates, and carbonates are insoluble except of those of alkali metals and salt and ammonia salts. So magnesium is not an alkali metal, so that's going to be a solid. This reaction goes to completion. So hopefully by this point you understand what each of these three terms means. You can determine whether something is soluble or insoluble by looking at those rules that we saw on slide 3. We can also predict the names of the compounds that are formed and identify which is going to be the insoluble precipitate. So if you have any questions, please let me know.